You've been told that your thoughts create reality. You've been told that quantum physics proves it. You've been told that observation collapses the wave, that consciousness shapes the universe, that manifestation is backed by science itself. Let me tell you something straight. You've been lied to. Not completely, but just enough. Enough that the actual truth, the real truth hiding right in front of us, has been buried beneath layers of pseudoscience, wishful thinking, and motivational sound bites that sound deep, but fall apart the moment you look closely. Here's what almost nobody tells you. Even the scientists who discovered quantum mechanics, the sharpest minds to ever peer into the foundations of reality, don't agree on what's actually happening. They can predict outcomes with breathtaking accuracy. They can build technologies that prove the mathematics works flawlessly. But ask them what's really going on beneath the equations, what reality itself is doing behind the scenes, and you'll get 8 different answers from 8 different physicists. And in this video, I'm going to show you why that isn't a problem. It's the entire point. Ready? Let's go deeper. Before we step into the battlefield of interpretations, I need you to understand something fundamental. Something that's going to give you real permission, not fake reassurance, but real permission to stop beating yourself up for being confused. The confusion isn't yours alone. It belongs to everyone. It belongs to Nobel Prize winners, to textbook authors, to researchers who have spent entire careers trying to understand what happens when a particle is measured. Because here's the truth, quantum mechanics works perfectly. Its predictions match experiments to absurd, almost unsettling levels of precision. But what it means, what's actually happening in reality, that part remains an open question. And not open as in, we'll solve it next year. Open as in, we've been arguing about this for over a century, and we are nowhere close to consensus. One of the leading voices in quantum theory said it plainly. To fully answer what's happening, we'd need a complete model of consciousness itself. Another physicist who developed an entire interpretation of quantum mechanics went even further. He said consciousness lies outside the scope of what quantum mechanics can solve. Let that sink in. The people who understand this subject better than anyone alive are openly telling you, we don't know. And this is where things get interesting. That lack of knowing isn't a failure of intelligence. It's not because the right genius hasn't arrived yet. It's because the question itself collides with something we barely understand at all. Consciousness, observation, the act of looking itself. So if you felt lost trying to understand manifestation, if you've struggled to reconcile spiritual intuition with scientific rigor, if you've wondered whether your thoughts actually do anything, welcome to the club. You're in very good company. The confusion you feel isn't ignorance, it's wisdom. It means you're paying attention. Now let me show you why this mystery matters. The problem begins innocently enough with what physicists call the measurement problem. And trust me, once you see it, you can't unsee it. Here's the setup. In the quantum world, particles don't exist in definite states until they're measured. Before measurement, an electron isn't here or there. It exists in what's called a superposition, a strange, ghost-like combination of all possible positions at once. The mathematics describes this using something called a wave function. Not a wave of water, not a wave of sound, a wave of probability, a wave of potential reality, and then you measure it. The moment you do, boom, the wave collapses. The electron snaps into a single definite position. All other possibilities vanish. One outcome becomes real. But here's the kicker. Nobody knows why. Nobody knows what actually causes the collapse. Nobody knows what truly counts as a measurement. Nobody knows where the boundary lies between the quantum world of superposition and the classical world of definite outcomes. This isn't fringe speculation. This is the central, unresolved problem of quantum mechanics. The thing that keeps physicists awake at night. One of the founders of quantum theory hated this so much that he created a thought experiment to mock it. You've heard of it, Schrödinger's cat. A cat sealed in a box, its fate linked to a quantum event. According to the math, until you open the box and observe, the cat is both alive and dead at the same time. Schrödinger wasn't saying, look how cool quantum mechanics is. He was saying, this is absurd. The mathematics is leading us to nonsense. And yet the math works, the experiments confirm it. Particles really do behave as if they exist in superposition until observed. The absurdity isn't imaginary, it's real. So what's actually going on? That's where interpretations come in. Because the equations don't tell you what reality is, they only tell you what you'll measure. Interpretations are attempts, competing, contradictory attempts, to answer the question beneath the question. What is reality? What role does observation play? Does the universe exist independently of us, or are we somehow involved in its unfolding? And here's what I want you to hear clearly. Every single interpretation runs into consciousness. Every one of them, not because physicists are trying to be mystical, but because the encounter emerges directly from the experiments themselves. You can't avoid it. It isn't a flaw in the theory. It's a feature of reality, so let's walk through the major interpretations. Let's look at what the experts actually say, and let's understand why, after a century of debate, there's still no winner. Shall we step onto the battlefield? The first interpretation, the one most physicists were taught, the one that dominated for decades, is known as the Copenhagen interpretation. Named after the city where its creators worked, it's elegant in its refusal to answer the deepest questions. Copenhagen says this: don't ask what's happening before measurement. The question itself is meaningless. Quantum mechanics doesn't describe what exists, it describes what we observe. Before measurement, there is no reality to speak of. The wave function isn't real, it's just a tool for calculating probabilities. And when measurement happens, the wave function collapses. How? Why? What qualifies as a measurement? Copenhagen doesn't say. It shrugs its shoulders and effectively tells you to shut up and calculate. And for a long time, that was enough. The math was so powerful, so successful, that asking deeper questions felt almost ungrateful. You want predictions? Here they are. You want technology? Take it. You want philosophical clarity? Sorry. Not included, but there's one thing Copenhagen can't escape. Measurement requires an observer. Something has to look. Something has to interact. And that something, whether it's a machine, a photon detector, or a human eye, is itself made of quantum particles. So where does the chain stop? When does the wave function actually collapse? One of the sharpest minds of the 20th century pushed this question as far as it could go. John Wheeler asked what happens if we follow the logic all the way down. He proposed an idea known as the participatory universe. The suggestion is unsettling and precise. Observers aren't just passive witnesses to reality, we're participants. Our observations don't merely record the universe, they help bring it into being. Not metaphorically, not spiritually, literally, in a physical sense encoded directly in the experiments themselves. And yet even Wheeler pulled back from the edge. He warned against reading too much into it. He famously said, observation, yes, consciousness, maybe not, and there's the tension. How do you separate observation from consciousness? What does it mean to observe without awareness? Copenhagen doesn't answer. It gives you a framework that works astonishingly well in practice, while leaving the deepest question suspended in midair. What is observation? And if everything is quantum, where does observation actually begin? Most people hate this ambiguity. They want solid answers. They want to know what's real. But Copenhagen's response is cold and simple. Reality is what you measure, nothing more, nothing less. In laboratories, in experiments, in engineering and technology, that's enough. Physicists even have a phrase for it, one they love to repeat. For all practical purposes, Copenhagen works, FAP for all practical purposes, but philosophers don't stop there. Mystics don't stop there, and people like you don't stop there either, because you're not just looking for a tool, you're looking for the truth beneath the tool. And that hunger, that refusal to settle, is exactly what gives rise to the other interpretations. So let's look at the one that goes in the opposite direction. The interpretation that says the wave function never collapses. Not once, not ever. The one that claims every possibility becomes real. In 1957, a graduate student named Hugh Everett proposed something so radical, so breathtakingly bold, that it took decades before the physics community even began to take it seriously. Everett said this: the wave function doesn't collapse, it never has. Every possible outcome of every quantum measurement actually happens, not symbolically, not metaphorically, literally. Reality branches, the universe splits, and every version of you, every possible you, experiences a different outcome in a different branch of reality. This is the many worlds interpretation. And before you dismiss it as science fiction, understand this. This is real science. peer-reviewed, debated at the highest levels. Many cosmologists and quantum theorists favor it precisely because it takes the mathematics completely seriously. Maybe too seriously, but seriously nonetheless. Here's how it works. When you measure a particle's position, nothing collapses. Instead, the universe divides. In one branch, the particle is here. In another, it's there. Both outcomes occur. Both universes exist. You don't see the other branches because you're embedded in one of them. No collapse, no mystery mechanism, no special role for observers, just the equations unfolding exactly as written. Every possibility realized, every quantum coin flip spawning new worlds. It sounds insane. And yet here's why it's compelling. Many worlds is fully deterministic, no randomness at the deepest level. No spooky collapse process, just a wave function evolving smoothly according to Schrödinger's equation. Everything that can happen does happen. We simply experience one thread of an infinite tapestry. Which means if many worlds is correct, there are versions of you making every possible choice. A version that said yes when you said no. A version that turned left when you turned right. A version living the life you dreamed about, and another suffering the consequences you avoided. Sit with that. Does it feel like freedom, or does it feel like existential dread? For some, many worlds is liberation. Every path is taken, every possibility honored. For others, it's terrifying. No single you, no privileged choice. Just endless fragmentation, identity split across countless parallel realities. And here's the catch. A big one. If every outcome happens, then no branch is special. No universe is preferred. The you listening right now is no more real than another you deciding to stop. Probability becomes nothing more than a counting measure. How many branches contain a given outcome, not a fundamental feature of reality itself. And consciousness in many worlds doesn't collapse anything. It simply rides along one branch, blind to all the others. So does that solve the measurement problem? Or does it just replace one mystery with another? Now we come to a third approach, one that tries to split the difference. An approach that says maybe collapse isn't mysterious at all. Maybe it's just physics we haven't fully calculated yet. This is decoherence. And it's the closest thing quantum mechanics has to a consensus, not because it answers everything, but because it explains something crucial that the other interpretations struggle with. It explains why we don't see quantum weirdness in everyday life. Here's the question decoherence tackles. If particles can exist in superposition, why can't large objects? Why isn't your coffee cup both on the table and not on the table at the same time? Why does quantum strangeness vanish as things get bigger? The answer is the environment. Nothing in the universe exists in isolation. Every object is constantly interacting with its surroundings. Photons bouncing off it, air molecules colliding with it, heat radiating from it. These interactions entangle the object with the environment in unimaginably complex ways. And that entanglement destroys the fragile coherence required for superposition. The wave function doesn't collapse. Instead, the superposition becomes so scrambled, so deeply entangled with trillions of environmental particles, that it becomes effectively unobservable. For all practical purposes, there it is again. The object behaves classically, definitively. This is decoherence, the process by which quantum possibilities are washed out by environmental noise. And it happens fast, unbelievably fast. For a dust particle, decoherence happens in less than a billionth of a second. For anything larger, the quantum world disappears instantly. So, problem solved. No collapse, just interaction, just physics doing physics, except not quite. Because decoherence doesn't actually solve the measurement problem, it just pushes it back, position. But here's the problem. The environment itself is made of quantum particles too. So when does its wave function collapse, or does it collapse at all? And if everything is entangled with everything else, the object, the environment, the measuring device, the observer, then where does the chain actually end? Decoherence tells you why you don't see superposition in everyday life. But it doesn't tell you what reality is. It doesn't tell you whether the cat is truly alive or dead before you open the box. It only explains why the superposition becomes unobservable. For all practical purposes, there's that phrase again. Decoherence is incredibly powerful. It works beautifully for building quantum computers. It explains how classical physics emerges from quantum laws. But does it answer the deepest question? No. Which brings us to the heart of the matter, the thing every interpretation runs into, the thing no one can avoid. The observer, consciousness itself. And this is where things stop being merely strange and start becoming truly profound. Let me tell you something most people don't realize. The role of consciousness in quantum mechanics isn't a new age add-on. It isn't pseudoscience. It isn't manifestation influencers hijacking physics to sell courses. It's real. It's unavoidable. And it's built directly into the foundations of the theory. So listen carefully, not to what motivational speakers claim physicists say, but to what the experts actually say themselves. One of the leading researchers in quantum decoherence stated it plainly. To give a full answer to the measurement problem, we need a model of consciousness. Not maybe, not someday, now. Consciousness is part of the equation. Two physicists who spent decades developing an alternative quantum theory wrote this. The intuition that consciousness and quantum theory are in some sense related seems to be a good one. These aren't mystics. They're physicists. Another researcher who developed the Ithaca interpretation went even further. He said consciousness lies outside the scope of what quantum mechanics can currently address. Not because it's irrelevant, but because the theory isn't yet capable of touching it. And then there's John Wheeler. Brilliant, careful, relentlessly rigorous. Wheeler proposed the participatory universe while simultaneously warning against mysticism. His position was precise. Observation matters, participation matters. We are not passive observers recording a pre-existing reality. We are involved. The universe does not fully exist until it is observed. But here's the paradox Wheeler couldn't escape. How do you have observation without consciousness? How do you separate the act of measurement from the experience of knowing? You can't. Not cleanly. Every interpretation runs into this wall. Copenhagen needs an observer to collapse the wave. Many worlds needs consciousness to explain why you experience one branch instead of all of them. Decoherence needs something to define when environmental interaction becomes measurement. Even the pilot wave theory, the Bohmian interpretation, struggles to explain how consciousness fits into its deterministic framework. This encounter with consciousness isn't optional. It arises directly from the theory itself and from neutral experimental demonstrations. That's not a quote from a self-help book. That's straight from the peer-reviewed literature. You cannot avoid it. So here's what this means for you, for your intuition that something is connected, for your sense that consciousness matters, for your suspicion that the materialist story, that reality exists independently and we're just biological machines watching it, is incomplete. You're not crazy. You're noticing something real. Something the experts themselves openly acknowledge. Universal connectedness isn't mysticism. It's Bell's theorem. Observer participation isn't manifestation hype. It's Wheeler's physics. That feeling that consciousness and reality are intertwined. That intuition is shared by some of the greatest minds in science. But and this part is critical, that does not mean your thoughts create reality like a cosmic vending machine. It means the relationship is deeper, more subtle, more profound than any soundbite can capture. So what are the implications of this? What does it actually mean for how we live? Let's go there. In 1964, a physicist named John Stuart Bell proved something that shattered our classical intuitions about reality. He showed that if quantum mechanics is correct, and every experiment says it is, then the universe is fundamentally non-local, interconnected, not in a vague spiritual sense. In a precise mathematical, experimentally verified sense. This is Bell's theorem, and it's one of the most profound results in the history of science. Here, what it means. If two particles interact and then separate, no matter how far apart they move, light years even, they remain connected. Measure one, and the other responds instantly. Not because a signal travels between them, but because they were never truly separate in the first place. They are parts of a single quantum system. Einstein hated this. He called it spooky action at a distance. He believed it meant quantum mechanics was incomplete, that hidden variables must exist beneath the theory. Bell proved him wrong, not with philosophy. With mathematics, there are no hidden variables that can restore locality. The universe really is non-local, and experiments confirmed it again and again with photons, with electrons. with increasingly sophisticated setups designed to close every possible loophole. The conclusion is unavoidable. Universal connectedness is real. But now listen carefully to what this does not mean. It does not mean your thoughts instantly affect distant objects. It does not mean you can manifest a parking space by visualizing it. Bell's theorem describes correlations between entangled particles. Not magic, not mind over matter. This distinction matters because the manifestation industry loves to cite quantum entanglement as proof, but they misuse it. Entanglement shows that reality is stranger than classical physics imagined. It shows that separability, the idea that objects are fundamentally independent, is false. But it doesn't give you telekinesis. What it does give you is this: a universe where everything that has ever interacted remains connected at a level deeper than space and time. A universe where the illusion of separation is just that, an illusion, where the boundaries between self and other here and there are useful but not fundamental. So ask yourself this: does that make you feel smaller or larger? For me, it's both. Smaller because I'm not separate, not special, not the center. Larger because I'm connected to everything, woven into the fabric itself, a single thread in an infinite tapestry. And here, that's where it gets even stranger. Some interpretations, like the transactional interpretation, suggest that causality itself may be bidirectional. That when you observe a photon from a star 100 light-years away, your eye sends a wave backward in time to the moment that photon was emitted. Not metaphorically, mathematically, the future influencing the past, the observer completing the loop. Is this true? We don't know. It's an interpretation, but the mathematics allows it. And that alone should tell you something important. Reality is far stranger than you were ever taught to believe. So let's come back to the question you're probably asking now. The question beneath all of this: what does this mean for me? For my life? For how I think about consciousness and reality? John Wheeler called it the participatory universe. The idea that we are not merely observing reality, we are participating in it. Our measurements, our observations, our interactions, they don't just reveal what's already there. They help determine what becomes there. But here's the uncomfortable truth. Participatory does not mean controllable. It does not mean you get to choose outcomes at will. It does not mean the universe bends to your preferences. It means you are involved in a process vastly larger, deeper, and more complex than your individual will. Think of it like a dance. You're on the floor, your movements matter, they influence the dance. But you're not dancing alone, you're dancing with partners you can't see, to music you didn't compose, in a hall you didn't build. Participation, yes. Control, no. And this is precisely where most manifestation teachings go wrong. They take the participatory universe and twist it into a promise. They tell you that because observation matters, your thoughts create reality, that consciousness is primary, that you are the creator. But that isn't what the physics says. And what the physics actually says is far more subtle and far more humbling. It says consciousness and reality are entangled in ways we don't yet understand. It says observation plays a role we cannot eliminate, but it does not say you are the author. That distinction is everything. One version turns you into a god, the other makes you a participant. One inflates the ego, the other places it inside something infinitely larger. And here's what I want you to really sit with. Maybe the mystery itself is the answer. Maybe the fact that we don't know, that even the experts can't agree, is telling us something essential. That reality is too vast, too strange, too multidimensional for any single story to contain. Wheeler understood this near the end of his life. He said our current understanding of quantum mechanics is probably like believing the Earth is flat before discovering it's round. We're missing something fundamental, something that once seen will change everything. So what does that mean for how you approach this? For how you think about consciousness and quantum mechanics and the relationship between them? It means you hold it lightly. You stay curious. You resist the urge to collapse the mystery into a sound bite. You learn to value the questions more than the answers, because the questions are what keep you awake, alive, engaged. One physicist said something beautiful near the end of his life. He said the attempt to understand quantum mechanics taught him one thing above all else: that reality is always more than we can grasp. That every answer opens new questions. That the universe is not a puzzle to solve, but a mystery to live inside. And maybe that's the real implication. Not what we can control, but how we relate to what we cannot. Before we close, I want to tell you something. This is episode 26 of the Observer Effect series. 26 explorations into the deepest questions reality offers. We've just spent nearly 30 minutes approaching the mystery from the physics side, from particles and waves, measurement and mathematics, from interpretations that still cannot agree on what's happening beneath the equations. But there's another side, the consciousness side, and in episode 27 we begin there. We approach the encounter from the opposite direction. Here is what I'm going to show you. Something that will make everything we just discussed even stranger. In the 1980s, a scientist named Benjamin Libet ran an experiment that shook our understanding of free will. He asked people to move their wrist whenever they wanted, a simple, spontaneous, voluntary action, but he measured their brain activity while they did it. What he found was disturbing. The brain showed a readiness potential, an electrical signature of decision, before the person reported consciously choosing to move. The brain decided first, consciousness followed later. And that raises a question so deep, so unsettling, that even physicists can no longer ignore it. Do you have free will? Or does your brain make decisions that consciousness merely experiences after the fact? In 2008, another researcher pushed this even further. Using brain imaging, he could predict which button a person would press up to 10 seconds before they consciously decided. 10 seconds. That's not a delay, that's a chasm. When asked what this implies, he said something remarkable. It doesn't rule out free will, but it makes it highly implausible. And here is where it connects to everything we've explored today. John Bell, the same Bell who proved universal connectedness, said something most people overlook. He said quantum mechanics cannot become a complete theory unless we assume experimenters have freedom. Free will isn't just philosophy anymore. It's appearing in equations, in peer-reviewed physics, at the foundations of quantum mechanics itself. And centuries earlier, a philosopher said something that sounds absurd until you hear it alongside modern science. To be, he said, is to be perceived. Nothing exists unless it is observed. When people mocked him, he had an answer, one that intersects directly with consciousness, observation, and the participatory universe Wheeler described. Episode 27 will take you there. Into experiments that challenge your sense of agency. Into philosophy that anticipated quantum weirdness centuries before it was measured. Into the hard problem of consciousness, a problem some physicists say may be as unsolvable as the measurement problem itself. We've been approaching from physics toward consciousness. Next time we approach from consciousness toward physics. And when those two paths finally meet, when you hold both mysteries at once, something shifts. Not because you finally understand, but because the question itself transforms. The playlist and the next episode are linked below. If this journey is calling you, if you're ready to go deeper into the encounter, I'll see you in episode 27. Until then, stay curious, stay rigorous, and stay awake to the mystery. This is Observer Effect, and the real observation is just beginning.